All right, so before starting section P2, you have to have section P1 more or less perfected. And in section P1, just for a few minute review, we had 3 rules of exponents. We had the rule that if you multiply terms with the same base, you add the exponents. And we did a bunch of problems that were, varying degrees of difficulty. This is kind of the easiest version, something like x squared times x to the 5th. This would be using multiplying terms with the same bases. And then we did that multiplication by adding the exponents. And then we did more complicated problems, maybe something like 3y to the 4th times 2xy squared. And in that kind of problem, it's still kind of the fits this rule, because I'm going to multiply the y's, and multiplying the y's, I'm going to add their exponents. And we would have done something like this. We could have dropped the parentheses, maybe inserted a times sign, and then because multiplications, you can shuffle around the order of the multiplication, I might have shuffled the order of the multiplication around. And then I'm going to multiply the like pieces together. I'd multiply the 3 and the 2 and get the 6. The x would stay alone. And for the y's, I'm multiplying the y's. These have like bases, so I add their exponents. So that was one of the 3 rules that we learned in section P1 that you still are going to have to know in section P2. You can't. That rule won't leave us, and it'll come back again. Another rule that we did is dividing terms with like bases. This is still just a quick review of section P1. And that's when we subtracted the exponents. And the most basic problem might be something like x to the 7th over x to the 3rd power. It's a division problem. Fractions are division. The bases for each of the numerator and the denominators are x's, and we do that division by subtracting the exponents, and we don't change the base. And then we had more complicated problems. We could have did something like 16 x to the 4th y squared over 12 x squared y. And I put this still in this category of dividing terms with like bases because I'm going to handle the x's and y's by subtracting the exponents. But the numbers, just like the numbers in the multiplication problem, I just did regular multiplication. In this problem, I'll do regular division. I'll go 16 divided by 4 is 4. 12 divided by 4 is 3. If you're not good at reducing fractions and you own this calculator, I just would have had to enter this fraction, hit the fraction button, and then did 16 in the numerator, arrow down to 12 in the denominator, and my calculator is going to tell me that 16 over 12 reduces to, I guess you can see that. I don't know if you really can. 16 over 12 reduces to, and you can't hardly see that 4/3, but it reduces to 4/3. So part of the answer is going to be 4/3, 4 in the numerator, 3 in the denominator. And then for the x, I'm going to subtract the exponents on the x's. I'll go 4 minus 2 for the exponent on the x. And for the y in the denominator had an exponent of 1. And for the y, I'm going to subtract its exponent. And an answer to this problem would be 4x squared y to the 1st, but I don't need to write the 1, over 3. So that rule's going to not leave us, and we're going to use it a lot in this section. And then the other rule that we learned in section P1, so this is still a review. Of section P1 is multiplying or raising, I'll say, one base to two exponents. And that's when we multiply the exponents. In a simple version of this, usually these problems all have parentheses. Something like x cubed to the fourth power, there's one base x, there's two exponents that apply to it. The rule that would allow me to simplify that would say this is x to the 3 times 4, which is x to the 12th power. A more complicated version might be like 2xy to the 4th cubed. And I put it in this category because I'm going to treat the letters by multiplying their exponents. The number 2, I'm going to cube. The x, I'm going to multiply the exponent of 1 that wasn't written by the 3. The y, I'm going to multiply its exponent 4 by the 3. So both the x and the y are kind of one letter or one base. The x is one base, the y is one base that have two exponents that apply to them. And that's when you multiply the exponents. This 2 cubed is 8. Then I'll get an x cubed and y to the 12th. So that is a really quick review and something you have to be really comfortable with when you get into section P2, because I'm going to assume that we're pretty good with all these rules, and if you don't understand the rules perfectly, the problems get a little harder in section P2 because the exponents will start to be negative numbers, and that just makes them harder. And if you don't understand the rules with positive numbers, then it's hard to transition smoothly into the rules with negative numbers. So if you don't understand P1 perfectly, don't watch P2 and get it down first. I'm going to split section P2 up into 2 videos. The first video is going to cover just problems 1 through 42, and it's on zero exponents. The second video covers from 43 to the end. It's like 43 to 140 something, and it's with the negative exponents. The second video is way longer than the first video, and it's a lot more complex. The first video, this covering the zero exponents, is supposed to be easy-ish, so hopefully it goes pretty smoothly. So generally, if I asked, a student about a negative x or zero exponent, I say this. Generally, we say anything to the 0 power is 1. And it's kind of unfortunate that we say that. While it's true, there's going to be times that that the rule doesn't seem to work. And I'll just kind of make 2 columns. So I can't, if I just blindly see a zero exponent in a problem and I write 1 down, there's a reasonable chance I'm going to write down something that's not right. Something like this, x to the 0 power, or -3 in a parentheses to a 0 power. These are going to equal 1, and as I get into the section, I'll explain why these equal 1. But this are 3 times where I have a zero exponent, but none of these equal 1. So this equals to 1, this equals to 1. Turns out that this equals to -1, this equals to -1, and this equals to 2. So, and you don't need to understand how I got those, but you just have to be at least aware that if I see a zero exponent in a problem, I have to do a little bit of thinking. I just can't say zero exponent it equals to 1, because that's not always the case. And for whatever reasons, math texts are loaded with problems that have zero exponents that don't equal to 1. Still not into the section, but I'll get there real quickly. And then, so let me just, say, why doesn't it even make sense for people to say this? So why do we say a zero exponent reduces to 1? And I can do it with an example as much as anything. So here's the example I'll use. I'll do 2 to the 3rd power over 2 to the 3rd power. My calculator can rock this pretty quickly, so let me do it on my calculator. Fraction 2 exponent 3 over 2 exponent 3, so that's 2 cubed over 2 cubed. And when I hit enter, my calculator tells me that it equals to 1 because that's what it equals to. If I didn't have a calculator, I certainly should realize that anything divided by itself was 1. Or I could have known that 2 cubed was 8. And this problem could be written as 8 over 8, and that certainly is equal to 1, because anything divided by itself, whether it's something as complex looking as 2 cubed over 2 cubed or as simple looking as 8 over 8 is equal to 1. So it's clear that 2 cubed over 2 cubed is equal to 1, but had I solved this problem using the divide to subtract rule, I should get the same answer. This problem can be solved many ways, and one of the ways I could have solved it is using the rule that we learned in section P1 for dividing terms with the same base. The 2's are the bases. I do the division by subtracting the exponents. And when I subtract the exponents here, I get 2 to the 0 power. It can't be the case that if I solve a problem using different methods, it can't be the case that my answers are different. So the answer to solving it this way, 2 to the 0, has to equal to the answer solving it that way. So we say that 2 to the 0 must equal to 1, because same problem, solved 2 different ways. If I solved it right both ways, the answers have to be equal to each other. And of course, I could just on my calculator enter 2 up arrow 0 power. My calculator is smart enough to know that that's equal to 1. My calculator is also smart enough to know when a 0 exponent isn't 1. It's just crappy today. You just can't see my calculator. So sorry about that. Sometimes you really have to fight to get it so you can see what I'm typing. So now I'm going to dig into the section and try to help you differentiate between when we get 1 and when we don't get 1. And it's not really going to be that hard. And after I get through the lecture, I'll maybe make a summary. So for part A of number 2, it's y cubed over y cubed. Well, that's clearly equal to 1 because anything divided by itself is 1. So I know that part A, this is equal to my answer is going to be 1 because anything divided by itself is 1. But had I solved part A by subtracting the exponents using the rule that we learned in section P0 and P1, it would have been okay. Had I written the answer is y to the 0, because that's a correct way to simplify the problem. So y to the 0 has to equal to 1 because anything divided by itself is 1, and solving the problem by a different method can't give a different answer. If the answers look different, they have to be equal to each other. So although it would have been okay to say my answer is y to 0, that's not preferred. Usually, if there's a 0 exponent in a problem, we're not going to write my answer with a 0 exponent. We're going to simplify it to get rid of that 0 exponent. But I do this little argument here because part B, the answer is just 1. Just a generic letter by itself without any parentheses, negative signs, just a generic letter to a power of 0 is equal to 1. That's one time we're going to get 1. So when do I get 1? So these are cases where a zero exponent equals to 1. And just a single letter, no negative signs, no extra numbers to a 0 power. That's the classic case where you get 1 for an answer. Number 4, 2 to the 5th over 2 to the 5th. Well, my calculator can do that pretty nicely. If I do 2 exponent 5 over 2 exponent 5, my calculator will tell me that that's certainly equal to 1. I didn't need to be a rocket scientist to know that the answer to this is 1, because anything divided by itself, whether it looks this complex or this simple, anything divided by itself is 1. 2 to the 5th is 32, just in case you didn't have that memorized. So an answer for this, and the best answer for this, would be 1. But I could have subtracted the exponents, because this problem is set up so that I'm dividing terms with the same base. And one way to simplify when you're dividing terms with the same base is to subtract the exponents. Had I subtracted the exponents, I would have gotten 2 to the 0. So it would have been correct, but not the best answer. To write 2 to the 0 for my answer. Which means that 2 to the 0 must equal to 1, because solving the same problem using different methods, the solutions you get have to be equal to each other. And that's why this 2 to the 0 power is just 1. This I could have done on my calculator as well. If I just did 2 exponent 0, my calculator will tell me that that equals to 1. So that's the next case, just a generic number. 2 to the 0 is going to be 1. And I can expand these, like z to the 0 would be 1, and 5 to the 0 would be 1. 115 to the 0 is going to be 1. And y to the 0 is going to be 1. So a single letter without a negative sign and a single positive number to the 0 power, they're all going to equal to 1. 6 is going to start messing us up. Nice thing about 6, doesn't have letters, so my calculator can do it. So 6a, if I do it, I see a 0 exponent, 5 times 4 to the 0 power, and my calculator says that 6a all of a sudden doesn't equal 4, it equals to 5. So my answer to 6a is 5 and not 1. So this is a case where I have a 0 exponent and I don't get 1. The reason it doesn't equal 1 is because orders of operations come into play here. And orders of operations tell me to do exponents before multiplication. So to simplify this, I'm going to do the exponent first, and then I'm going to multiply. The exponent, when I do it, it's going to change the 4 to the 0 power to 1. And then I'm going to multiply. And 5 times 1 is going to give me what my calculator knew the answer was, which was 5. 6b hardly looks different than 6a, but it certainly is a lot different than 6a. When I go to do 6b, if I break my calculator out to do this, I'll go parentheses, 5 times 4 parentheses, exponent 0 power, and my calculator tells me that equals to 1. So the problem almost looks the same, but now I get 1 as opposed to 5. There's a complicated way to look at it and a non-complicated way to look at it. The complicated way to look at this is if I have an exponent outside of parentheses that only has multiplication, I can take each of the numbers and raise it to that power. So this is kind of using a skill that we learned in section P1. When you have multiplication inside of parentheses and an exponent outside of it, you're going to raise each number to that exponent. And now this is going to be 1 times 1, which is 1. That's too complicated. The rule that we're going to learn is if we have a zero exponent outside of parentheses, the entire parentheses reduces to 1. So the big difference between 6a and 6b are that parentheses. The parentheses is going to make ones happen. So the second case where we're going to get zero exponents equal to ones. The first case is just a generic letter or a positive number to a zero exponent. The second case that we're going to get 1 is if I have a parentheses with a zero exponent outside the parentheses. Regardless of what's inside a parentheses, if you have a parentheses with a zero exponent outside of it, whether that parentheses is a fraction or not, if you have a parentheses and a zero exponent outside of it, that turns into 1. So first case where we get zero exponent, that we get 1, just a generic letter without a negative sign or a positive number to the 0 power, you get a 1. A parentheses, regardless of what's inside the parentheses, if it has a 0 exponent, it's 1. Like something like even this, -3 to the 0 power. This is a parentheses with a 0 power, that's going to equal to 1. 6a didn't follow in that rule. 6a, the 0 exponent didn't apply to the parentheses, it only didn't apply to the 5, it only applied to the 4. 8a is a lot like the a of 6. If I do 8a, I go -1 times 2 exponent 0, and my calculator knows that 8a is not equal to 1, it's equal to -1. Because to do this without my calculator, for orders of operations, I need to first do the exponent. The exponent is the 2 to the 0. The exponent of 0 only applies to the 2. So this is going to be -1 times 1, and then I'll multiply. Part B, this fits the rule. If everything in a problem is in a parentheses with a 0 exponent outside of it, that's all going to be turned into a 1. So let me do that on my calculator real quick, just so I can show you that simplified rule works. Anytime I see a parentheses with a 0 exponent outside of it, and that's what I just created right there, created problem 8b, fits my rule where if I have a parentheses, regardless of what's inside the parentheses, how simple or complex it is, could be as simple as a single negative number, could be as complicated as a fraction. If I have a parentheses with a 0 exponent outside of it, which I have here in part B, that whole thing reduces to 1. I don't know if you can actually see that, but reduces to 1. So this is equal to 1, and I shouldn't put any thought into that. If I see either one of these scenarios, a positive letter or a positive single number to the 0 power, or a parentheses with a 0 exponent, immediately I'm going to just pop a 1 in for those. But if I don't see that, and that's not here, this is not the same case, because the -1's not in a parentheses, the exponent doesn't apply to the -1. This is the evil trick. On A, my calculator is not going to be tricked, because if I do negative in the parentheses and then 2 exponent 0 tells me the answer is -1. You'll notice in my shortcuts of when I look at something and know that it's equal to 1, I didn't have any negative signs. And it's actually the case that if I put a negative in front of these, like if I did negative x to the 0, or negative y to the 0, or negative 5 to the 0, or negative 115 to the 0, these actually all equal to -1. The reason that is it's an order of operations, and it's a tricky problem. It's a tricky problem that mathematicians throw in books all the time. Problem A of number 10, I need to think of this as -1 times 2 to the 0. That negative 2 to the 0 means -1 times 2 to the 0, and the only thing that's being raised to the 0 power is the 2. 2 to the 0 power is equal to 1, and then -1 times 1 is the -1. -1 times 1 is -1. Part B, this is in the bottom, well, part B is screwed up. Part B, this 0 should be right here, so I'm going to fix this. So when you print yours out, it'll look like this, because that was a poorly written problem. Part B should have been written like that, and I'll fix it before you watch the video. Part B, fixed part B, that is this kind of problem. It doesn't matter how simple or how complicated the inside of the parentheses is, but if I have a parentheses with a 0 exponent, that whole thing's going to be equal to 1. And again, my calculator can do this if I just go parentheses -2, using the negative in the parentheses, exponent 0, my calculator gives me that that's equal to 1. Because if I have the entire contents inside a parentheses with a 0 outside the parentheses, that will reduce to 1. But negative numbers or negative letters without the parentheses aren't going to equal to 1. So if I had just changed those problems, like -x to the 0, or -y to the 0, or -5 to the 0, once I toss a parentheses and encapsulate that negative inside a parentheses, then I get 1. So this is a big subtle difference, because these problems feel like these are just raising something to the 0 power and I should get 1, but none of them work that way. And like this -5 to the 0, I could have checked on my calculator. I did -5 exponent 0, and my calculator will tell me that that's equal to -1, because that is what it equals to. So that's a big target that I'll put on the test, I guess. I'll be able to differentiate between when you get 1 and when you don't get 1. And the only times that you get 1 is if you have a single positive letter or a single positive number. It's really bad saying that's a positive letter, because I don't know what X stands for. But if you have a letter without a negative sign and a number without a negative sign to the 0 power, that equals to 1. But if you have negative signs and a 0 exponent, you get -1 unless the negative sign is inside the parentheses. Then that'll revert. This rule will supersede it, regardless of how complicated the inside of a parentheses is. If you have a parentheses with a 0 exponent outside of a parentheses, that whole thing reduces to 1. So for 12, A is not the case where I'm going to get 1, because this means -1 times 1. The only thing that's being raised to the first power is the x to the 0, and my answer to part 12A is going to be -1. 12B, it's going to fit the rule that the entire contents of the parentheses are being raised to the 0 power, so that's going to be equal to 1. So the parentheses are so key to making something equal to 1 when we're dealing with with negatives and 0 exponents. 14A and 14B, I can't use my calculator to do. 14B fits perfectly the case something to the 0 power is equal to 1. If it's inside a parentheses. For the contents of the problem, there's nothing outside the parentheses, and I have a 0 for the exponent outside the parentheses. That's equal to 1. Part A, this really means -1 times x to the 0, which really means -1 times 1, and the answer to 14a is going to be -1. So that's this big differentiation. If you have a single letter with a negative sign or a single number with a negative sign, if the negative's not in a parentheses is equal to -1. If the negative's inside the parentheses is equal to 1. 16 I can do both on my calculator, but I hardly need my calculator at this point maybe to do them. So for 16a, if I go 3 times 4 exponent 0, the answer for this is 3. For b, if I go parentheses 3 times 4 exponent 0, the answer to that is 1. And so by now, hopefully you're starting to be able to recognize when something is a 1 and when something isn't a 1. Something isn't a 1 when we don't have a parentheses, because in 16a, the only thing that's being raised to the 0 power is the 4, and then I'm going to multiply it by 3. So I'm going to get 3 times 1, which is 3. But in part B, when the entire contents of a parentheses are raised to the 0 power, that equals to 1. 18, I couldn't do on my calculator, but it's the same trick. 18a isn't going to equal to 1 because the 3's not in a parentheses. I think of this as 3 times y to the 0, which is 3 times 1. The exponent of 0 doesn't apply to the 3 when the 3's not in a parentheses, and only the y to the 0 turns into 1, and then I multiply by 3. So the answer to 18a is going to be 3. Whereas b, the entire contents, both the 3 and the y are in the parentheses with a 0 outside, that's when I get a 1. 20 is kind of hammering on this trick and making the problem a little bit harder. I think of this as 4 times a times b to the 0, and the only thing that's being raised to the 0 power is the b. So this is really 4 times a times 1, because the b to the 0 is the only thing that turns to 1. And here I multiply the 4 and the 1 and get a 4, and I leave the a. So the answer to 20a is going to be 4a. And then part b, if the contents are in a parentheses with a 0 exponent, that's when you get a 1. Because this is really 4 to the 0, a to the 0, and b to the 0. I'm raising each thing to the 0 power. Everything in the parentheses needs to be raised to the 0 power, and so they all turn into 1. You get 1 times 1 times 1, which is 1. 22a, I think of this as 3 times a to the 0 times b. The a to the 0 turns into 1, so I get 3 times 1 times b. And for an answer, I'm going to write 3b. 22b fits my mold. Even though I've got a 0 exponent inside and outside the parentheses, it hardly matters. The contents of the parentheses are irrelevant. If I have a 0 exponent outside of a parentheses, I'm going to turn that to 1 without even thinking. '24 and 26 are beautiful. They're just a single letter, positive, no negative signs, single number, positive, no negative signs, no parentheses. Those are classic examples of ones. 26 I could have done on my calculator. 24 I couldn't have done on my calculator, but that's the kind of problem where I'm going to immediately toss down a 1. But between 28 and 30, I have to be careful. 28 is not going to give me a 1. In fact, if I did it on my calculator, I'd go -2 exponent 0, and I'd actually get a -1. You can see it, yeah. And that's fitting this mold right there. I have a negative and then a number to the 0 power without a parentheses. Those equal to -1. You should just start to recognize that those equal to -1, but you could remember that this means -1 times 2 to the 0. Only the 2 to the 0 turns into a 1, and this whole thing reduces to -1. And then problem 30, as long as the contents of the parentheses are raised to the 0 power, you get a 1. 32 and 34, same sorts of problems. 32, this is really -1 times t to the 0, which is -1 times 1. The answer to 32 is -1, and 34 fits the mold. The entire contents of the parentheses are being raised to the 0 power, so that's equal to 1. 36, I think of this as 4 times b to the 0. Only the b to the 0 is equal to 1, so this is 4 times 1. My answer to 36 is going to be 4. In 38, the entire contents of a parenthesis raised to the 0 power, you get 1. So the 0 power, once you learn the separation and the tricks, you know, the only times I'm going to get 1s if I have a single letter or a single number without a negative sign raised to the 0 power, or if I have a parentheses with a 0 exponent. If I don't have one of these two cases, a single letter or a single number without a negative sign raised to the 0 power, or everything in a parentheses raised to the 0 power, if I don't have one of those two cases, then it's not going to be 1. And the biggest trick is the negative without the parentheses. The negative single letter or negative single number without a parentheses to the 0 power is -1. .40, I think of this as 4 times a times b to the 0 power, and only the b to the 0 power turns into 1, so that's 4 times a times 1. I multiply the 4 and the 1 and leave the a, and I get a 4a for my answer. 42, the entire parentheses is raised to the 0 power, so that's equal to 1. That's the entire beginning part of section P2. That's the easier part. Just being able to pick out when something with a 0 exponent is equal to 1 and when something with a 0 exponent isn't equal to 1. It's an important skill, but it's not like a hugely important skill. There'll be a problem or two on the test, but it's the less important part of section P2. The second part of P2, the stuff with the negative exponents, it's more complex and a little more important. So make sure you get this part of P2 down and you have all of P1 down, the rules that tell me when to add the exponents, subtract the exponents, and multiply the exponents. They're going to come much more into play in the second half of P2. And the 0 exponents, they don't come up in the second half of P2. So hopefully you feel comfortable now of when you see a 0 exponent, when you can write 1 and when you don't write 1. And if you got that out of this part of the lecture, you know everything you need to know. All right, so I'm going to shut it down here, and I wouldn't expect you to do both parts of section P2 using at the same time, because it's going to take a lot of time. The next video, I bet you it's an hour and a half long, and usually you should spend double the time watching the video because you're doing homework while you're watching the video. So an hour and a half for me to do the problems and explain the theory, and an hour and a half for you to do the problems. You should plan to have about 3 hours when you're watching that video over the second half of P2.